For this video, which I may split into two if the solution takes a while like the last one did, I have another practice problem planned. So this one is derived from example 12.2 in the Visco textbook. It asks you to use the Peng-Robinson equation of state to predict the PXY diagram for propane and butane at 323.15 Kelvin. So in this problem, we don't have any experimental data, so we're going purely based off of prediction. So this prediction is as good as the Peng-Robinson equation of state accurately models the vapor and liquid phase for propane and butane. So I've clipped this from the notes. I'll discuss it quickly just to recap it. It's going to be very helpful for establishing our algorithm moving forward. By Gibbs phase rule, we have two components and two phases. So 2 plus 2 minus 2 is equal to 2. So we've got 2 degrees of freedom in terms of how we solve this problem. We are asked to predict the PXY curve, therefore we must set temperature, which the problem statement has done for us. So we've got 323.15 Kelvin. The other choice of what to set will be either one of the compositions. So we could either set X or set Y, and then if we set X, we have to calculate the bubble point pressure, then we can calculate Y after that. If we set Y, we can calculate the dew point pressure and then calculate X after that. So either or will work. Traditionally, I prefer to do the X because the bubble point calculation is a little bit easier, just by slightly. And also, I don't know why, but I prefer to set X every time. Just personal preference, like I said. So we've got 3 equations, 3 unknowns, a system of 3 equations. The first 2 equations are the phase equilibria relationships between the 2 components. So we're starting off with the mixture fugacities of the 2 phases must be equal, and then simplifying from there. So this is, the first equation is the phase equilibrium relationship for component 1, which we'll assign to be propane. The second one is the phase equilibrium relationship for component 2, which we'll assign to be N-butane. And the third is that the pressures of the 2 phases must be equal. So again, this is oftentimes one that we take for granted, but one that we will have to explicitly state as we move forward. So moving on to what the Peng-Robinson equation of state says about fugacity. So if you look at these 3 equations, we have a lot more things that we have to calculate than meets the eye. So we've said that we're going to set temperature, and I will set X. So we'll treat X as a known parameter. The 3 unknowns that we have are the pressure of the vapor, the pressure of the liquid, and Y, the vapor phase composition. So that is insinuating that we do know what the mixture fugacities are for the liquid and for the vapor phases for the 2 components. So we need to have the equations from the Peng-Robinson equation of state handy. I've pre-done that, so I've looked up in my notes again where I've had the mixture fugacity expressions. For Peng-Robinson, it is this long equation. So what we're going to need is Z is PV over RT. So pressure is going to be involved in this equation, which we do not know. I'm looking for new unknowns here. So BI and BM, we're going to have to look up what those are. Remember, BI is the Peng-Robinson parameter. So we'll have an equation for that. BM is the mixture parameter. So there's an equation to calculate that as well. B is not a function of any variable though. So BI is purely a function of the critical temperature, critical pressure, and the acentric factor. BM is a function of what the 2 pure component parameters are, and of X, which we'll have, right? So no new unknowns are introduced there. Z, as I said, is PV over RT, so no new unknowns introduced there. A is the same as B, so we'll have to calculate that based on pure component properties. And that's it, right? So this is a fairly long equation that will give us the mixture fugacity coefficients, but no new unknowns there. And then by the Peng-Robinson equation, again, this is just the Peng-Robinson equation for each one of the phases, so we'll have to calculate what PL and PV are, and we'll set these 2 things equal to each other. So same equation, just with a different subscript every time for liquid and vapor phases. And then these are the expressions for the mixture Peng-Robinson parameters. So we'll have to look up what A1, or calculate rather, what A1 and A2 are, and B1 and B2. And from that, we can calculate what the rest of them are. Remember, we can adjust this a little bit by taking into account you can fit this parameter K12 with experimental data. because we don't have any experimental data, I'm going to assume that K12 is 0 and just simplify it by taking the mixture. So this term will just drop out and we'll leave it with the regular expression. All right, so the first thing to do then, it would seem, is to calculate. We need to look up some properties for propane and butane, and we need to calculate what the B1 and B2 parameters are. So I'm going to do that in Excel, and I'll see you when I've got that done. All right, so I've looked up the relevant information. I looked this up in the back of Dom and Visco, so you may have slight disagreements, but in general, you should have close to the same things that I've got. I've taken care to convert the critical pressure into pascals from bar. So remember, my brain likes to work. I always like to use SI units. So regardless of the fact that I have a huge number here numerically for PC, having it in pascals is going to be helpful because I can always use 8.314 for R. So I'm just multiplying by 100,000 to convert bars to pascals. And then to calculate the Peng-Robinson parameters, A and B, for the pure components, I have to look into the Peng-Robinson lore a little bit. So this is in either textbook, either Sandler or Dom and Visco. Look up in where they first introduced Peng-Robinson, and you can find expressions for the A and B parameters. So the parameter A is a function of another parameter, kappa, which is defined as 0.37464 plus 1.54226 times omega minus 0.269932 times omega squared. I always wonder if all these significant digits are actually necessary. I keep them just in case, but I really wonder about that sometimes. So I'm copying the same formula down so that I don't have to type it twice. Kappa is just a function of omega, the acentric factor. And then I have another parameter, alpha, here, which is a function of kappa and the reduced temperature. So before I do alpha, maybe I want to calculate what the reduced temperature is. So TR, and this is equal to T, so 323.15 divided by the critical temperature. All right, so that's going to help save me a couple keystrokes in the next expression for alpha. And alpha is 1 plus kappa. Oops, I forgot my equal sign. Always got an equal sign. 1 plus kappa times the quantity of 1 minus the reduced temperature to the 0.5. And then this whole thing gets squared. All right, just double checking. I know I made a mistake last time that cost me big time, so I'm just going to double check as I go. All right, seems good. That's my alpha parameter. Now, let's see. AC is a separate one again, A sub C. So this is equal to 0.45724 times 8.314 square times the critical temperature square and divided by the critical pressure. So once again, these formulas that I'm typing now, I didn't write them just because they're from a previous chapter of the textbook. Just look them up. That's where all these funky numbers and parameters are coming from. Okay. All right, so finally, I'm able to calculate my parameter A. So this is my van der Waals parameter A. And I had caps lock turned on, so I need A and a B. A is just alpha times AC, and B is 0.07780 times R, 8.314, times critical temperature, not the reduced temperature, critical temperature divided by critical pressure. Okay, just double checking one more time. I think I'm okay. All right, copy that down. All right, so these are my pure A's and B's. Now, in order to calculate what my mixture A and my mixture B are, I'm going to need the composition as well. So these are going to get shaded. I like blue. Blue is one of my favorite colors. So let's do all borders to highlight them a little bit more. All right, and that'll keep them fresh in my mind whenever I want to calculate them. So I said I'm going to set x's. So x is going to be the variable that I elect to set. You could also do y's, I'm pretty sure. So I'm going to make a table for my x's. And as I like to do, I'm going to set this equal to 0 and then say that everything else is equal to 0 plus 0.2. And I'll do 50 data points. And that's a pretty good number. All right, going all the way down until I hit x is equal to 1. All right, now that I have a table of x's and I want to center this just so that it looks nice. Okay, now that I have my x's, I can calculate theoretically what my mixture parameters will be. So I paused there to kind of figure out what my organization of my sheet that I want. I think I'm going to want to do y's there next. Remember, I don't have what y is quite yet, so that's going to be something that I have to solve for. But if I have x and y together, I'm going to like that. I'm also going to have, actually, you know what? I want to put pressure here as well. So pressure is something I'm going to have to solve for. So y and pressure in pascals. All right. Okay. Calculating what my AM for the vapor phase is then. So can't do subscripts and superscripts very easily, but AML. So AMV and AML. So I'm just going to use this same expression. I don't know what y is quite yet, so I'm going to just leave it as a placeholder. So y1 squared, whoops, y1 squared times a1. So this is a1 and $sign it plus 1 minus y1 squared times a2 plus y1 times 1 minus y1 times square root. That function call is sqrt a1 times a2. Close, close. Typo in the formula. That is never a good sign. Let me see. Oh, wait, did I only have to close once? Yeah, I only had to close once because these things are all being multiplied together. All right, that should be okay for AM of the vapor phase. So I'm going to have a formula here for Y. So this is not going to mean much at this point. I don't expect it to be correct because I don't have my Y's filled in. I'm just making sure that everything is going to be consistent. Or everything's going to be set up so that when I calculate it, it's going to reference the proper cell. AM for the liquid phase is x1 squared times a1 $sign plus 1 minus x1 squared times a2 plus x1 times 1 minus x1 times square root of a1 times a2. And this one should be correct, right? Yep, so this one is going to change as I go down. Now, B of mixing for the vapor phase is going to be similar to A of mixing for the vapor phase, where I can't actually calculate what it is yet. Y1 times B1 plus Y2, 1 minus Y1 times B2. And BML, similar, but for X. So X1 times B1 plus X2 times B2. All right, copy both of these down. And now I have formulas at least. I don't know what the exact parameters are. I'm going to have to use solver later on. So I'm going to get rid of this and move on to the next step. Okay, realized I misspoke a little bit when I said unknowns. My unknown is actually not pressure of the liquid and pressure of the vapor. It's molar volume of the liquid, molar volume of the vapor. I'm going to fix that real quick. Whoa, that was weird. V, L, I don't know what's going on with my stylus. These are my unknowns, and Y is my other unknown. So molar volume of the liquid and molar volume of the vapor are going to need to be two other columns that I will have to solve for. And those are going to come into play in the Pang-Robinson equation of state. So I've got Z, which is PV over RT. And for each one of the phases, I'll use the molar volume of that phase. The other thing I'll need is the A12 parameter, which is going to be the square root SQRT of A1 times A2. All right, so I'm going to need this in my mixture fugacity coefficient equation. Okay. Next, I want to code up my formulas for my fugacity coefficients. I'm going to have 4 mixture fugacity coefficients. I've got one each for liquid and vapor and one each for the 2 components. So I'm going to do Phi1 liquid. This is Phi hat, just try to be as proper as possible in terms of my notation, and Phi1 vapor. So I'm going to go in the order that I have them in the equation. So Phi1 liquid, Phi1 vapor, Phi2 liquid, Phi2 vapor. Phi hat 2 liquid, Phi hat 2 vapor. All right, so I'm just going to, again, use this one equation, and in whatever phase that I have, I'm going to calculate the mixture fugacity based on that. So here it goes. Equals exponent. So the whole thing has to be exponentiated. So B1, BI is B1, and that is in neither the liquid nor the vapor phase. So I could just take B1 there, $, divided by, no, I want to multiply it by Zm. Now Zm is going to be pressure, which is going to be in that cell, times molar volume. And this is of the liquid phase, so I want to take the molar volume of the liquid phase. I8 divided by R times T, 8.314 times T, 323.15. Where once again, I could put the values of R and T in a cell, but when I write out in the keystrokes what it is, it's a little bit more obvious of what it is. Remember, I could also name the variable in the sheet if I want to, so that it's just R times T. I could literally write R and T if I name the variable like that. Anyway, I won't do that. I don't typically do that, by the way. It's more trouble than it's worth, just in my opinion, but you might find it helpful. -1, and then that closes out this parenthesis, divided by B for the mixture. So this Bm has to be B mixture for the liquid phase, because we're doing the phi of the liquid phase. So that one. And then minus ln, so going on to the next term here, minus Zm. And I almost wonder if it's worth it at this stage to, I might do that. I'm going to do exactly that. So instead of writing out Z every time, I'm going to make a column for Z. So I'm going to leave this formula as it is and shift everything. This is, again, what I like to do. It saves me keystrokes. So Z compressibility of the vapor and Z compressibility for the liquid. So Z is going to be equals P times V. Whoops. Oh, I don't like what I did here. I'm going to want to, I'll show you in a second. I want to keep it consistent. So reduce mistakes as much as possible. I need to rewire, oh, but I've already done liquid vapor first here. All right, I'll keep it. I'm going to do vapor first, then liquid. All right, so vapor first, then liquid. Phi to vapor, Phi to liquid. And again, sorry I don't have these pre-done. There's many reasons for that. As you can see, like this is a very long problem to solve, so it would take me a very long time to solve it, and then to undo everything in order to redo it for the class, I think would be a big commitment for me. But also, I hope you're finding this very informative as I'm kind of going through it in real time. You're hearing me think out loud. So how I would solve the problem is what you're being able to see. So hopefully that's helpful. I'm really curious to see if you agree with that or not, or whether or not the next time I teach this class, maybe I will try it the other way. Or since I already have the Excel spreadsheets, maybe I should try and do more of them pre-made. Anyway, back to Phi 1 vapor. That's the one I want to do first. I'm getting confused. I got sidetracked there. I want to calculate Z first such that I can just plug in Z whenever I need to. So Z is pressure times molar volume divided by R, 8.314 times T, 323.15 Kelvin. Okay, and 0 is not surprising there because I don't have anything in P or V. And Z for the liquid is P times V of the liquid divided by 8.314 times 323.15. And that's not an asterisk, that is supposed to be a parenthesis. All right, copy that all the way down. Okay, now Phi 1 for the liquid. Let me see if I can style, yeah. I don't want to be able to see through it. Phi 1 vapor equals exponent. But the bad side is I've deleted everything I've had so far. So B1 $ times, now this is going to be much easier to type now, Z mix, or Z of the vapor, minus 1, minus ln of Z minus B mixture for the vapor. So that's in this cell, not $, importantly, times P, and P of the vapor is equal to P of the liquid, so there is no subscript there that I have to worry about, divided by R times T, 8.314 times 323.15. Okay, close out the denominator, close out that ln, and then minus AM. This is just AM. Which AM is that? Oh, so we're doing for the vapor phase. So I want AM for the vapor phase. And for this one, I'm going to do the coefficient by itself. So I'm going to parentheses D8 divided by 2 times SQRT2 times B for the mixture, that's of the vapor phase, times 8.314 times 323.15. And, oops, I don't want, do I want to close that out? Yeah, I do want to close that one out. And then multiply that. So this term gets multiplied by this thing in parentheses. So times, let's see, I'm going to want to open parentheses again. 2 times open parentheses x1 times A11. So A11 is equal to A1, right? So that's kind of confusing notation, right? But I'm going based on subscript. So because I'm calculating Phi 1, I substitute a 1 for this I, and I get A11, which is equal to A1, plus 1 minus x1, which is x2, times, now this is A12, so I have to take the cross term there. So this, I'm pulling A12 in this case. So that gets $. Now, I have a lot of terms here and I don't want to make a parenthesis mistake. So I want to close out the purple one and divide that by A mixture for the vapor. Minus B1 $ divided by BM for the vapor. Now this one should close out that one by the 2. All right, so red and red go together. Times ln of Z, just for the vapor. So that's in J8. And my formula is now so long that I can't even click that term anymore. Plus, I'm going to want more parentheses here. Parentheses, Zm plus 1 plus SQRT2 times Bm, oh wow, times G, no, FBMV, F8 times P divided by RT. Oh, no, I don't want to accept a correction. I'm not finished yet. 8.314 times 323.15. That's just the numerator. All right, so I need to close out the purple and divide that by, oh, what's the difference between the top and bottom there? I think I made a mistake there. Let me check that. I did mess this up. I had another mistake. This is a minus. So 1 minus square root of 2. So the bottom is almost the same. So it's Zm, so it's J8. I really hope I don't make a mistake, but I probably have. J8 plus 1 minus SQRT2 times B mixture vapor F8 times P divided by 8.314 times 323.15 Kelvin. Close out everything now. I think that's it. Let's see, number mistake. Yep, I made a mistake somewhere. All right. Tell you what, this video I think is getting pretty long. I have to go now because we have class that is occurring pretty soon. So depending on how long this video is, I may or may not continue this today. Maybe we'll pick this up on Wednesday, but this may be another situation where I have to kind of look at it a little bit and evaluate where my mistake is, because I'm not going to be able to go through this right now and see where my mistake is. So we'll stop this video here for today. We may or may not have another video for today. I'll evaluate after class today. See you soon.